Chalo, come on everyone. So last thing we were doing was an echo. Okay, let's do a problem on this. Let's say we have a tall building. There is a wall. So we have a person here who jumps from the building. Gravity is there. Distance between the wall and the building is d. While making a noise at t is equal to 0. Means he just shouts once. C is the speed of sound. Find the time when he hears an echo. Now see, if he was just standing here and he shouts, now the sound will go like this, hit the wall and come back, isn't it? But when he is jumping, that sound wave won't come only. Now how will that sound travel? He made a sound. See, when you shout, it doesn't go in one direction, it is going in all directions, isn't it? So as this person is falling, the sound which got reflected somewhere here, so this person is falling, the sound is traveling this way, it gets reflected and comes here, and it meets him. You getting it? So the reflected sound from the wall will meet him after some time. Find the time when he hears an echo. I can even ask this thing, find the condition if it doesn't hear an echo. Let's get this. Mostly a kinematics question. Others do keep your cams on. How do we do this? So this person falls in a straight line. Let's say they meet somewhere here. Now this sound here will travel something like this. So that means the sound which went this way this is the sound wave. So he hits the wall and it bounces back and then he hears somewhere here. So this is the point where he hears an echo. Now from principle of reflection, we know this angle and this angle are equal. So that we have the principle of reflection there. And how much height will he fall? In time t, this guy will fall a height of half gt square. Isn't it? S is equal to ut plus half at square, u is 0. So in the same time, how much did the sound travel? So if this distance is d, and this distance is half gt square, so this is what we are getting. So this was d, and this is 1 by 4 gt square. So if we call this thing a, b, and c, so time taken for the sound will be ab plus bc by the speed of sound. This is nothing but 2 times root over d square plus 1 by 4 gt square ka whole square by c is again time t only, is the same time. Square it on both sides, you end up with c square t square 4 d square plus 4 g square t power 4 by 16. You get a biquadratic. So we have g square t power 4 by 4 plus c square t square minus 4d square equal to 0. So t square is equal to minus c square plus root over c power 4 plus 4g square d square. Did I miss out on something? ये minus था बीच में. ये plus था. Yeah, that's minus 4g d square by g square by 2. So there are two roots, right? Plus or minus. So both the root, there are actually two roots possible here. That means we thought it is only one time, but the max is saying there is one more sound wave which will hit here, which will reach him here again. So this thing can have multiple answers. We can have two answers, we can have one answer, and if c power 4 minus 4g d square or g square d square, if this is less than 0, means you won't hear an echo. Clear with this? Like I said, it's mostly kinematics question, there's nothing there. But the main thing here is this sound here will behave like principle of reflection. And like we thought there'll be only one answer, but there is a possible of getting two answers. And if c square becomes equal to 2gd, you'll hear only one echo. If it is less than that, you will not hear any echoes. So this is c is less than root 2gd. This is a condition for not hearing an echo. All clear with this? Yeah, so mostly a kinematics thing. Next one. Any doubts on this? Intensity of sound waves.
So, but if the man is traveling faster than the speed of sound, then without solving only we can say that there'll be no echo, right?
Man is traveling with speed of sound, but man is initially jumping with 0, right?
No, like, oh yeah, that's true.
You could have heard the echo before reaching that speed, na?
Right.
Yeah. Actually, now I think here something like that is only happening. The first time he's falling, right? He heard this echo, this sound which went away, right? Because he's going so fast, eventually he'll go and catch up with this sound once more.
Gotcha.
Something of that sort was happening. Next thing, intensity of sound wave. Now, the same formula which we derived there in strings is valid here. Intensity is R for rho, not mu. Mu is for power. A square, omega square, V wave. We also know delta P max, but every time they might not give in terms of, A and omega. Sometimes they might give in terms of pressure. So we can replace this amplitude with BA by K. Sometimes I don't want to give V wave also. So in that case, we have to use B by rho. So these are the three main formulas that we had so far. So depending on what quantities are given in the question, you can manipulate and use them. So this is the intensity, but this is not really a good way to study because the intensity can vary a lot. So what we do, we use something called decibels. You must have seen this on a speaker and everything. It will be written in terms of decibels. Just like, we study acidity pH scale. Even though the main concentration is H+, we study the pH scale. So decibels is also something similar. So beta, that is the symbol for decibels, is given by 10 log intensity I by I naught. This is also log scale. So I is intensity, I naught is a constant, which is 10 power minus 12 watt per meter square. You need to mug up this. Example. Let's say if I is 10 power minus 6 watt per meter square, then your decibels would be 10 log 10 power minus 6 by 10 power minus 12. This turns out to be 60 decibels. Straightforward one. So in our mains or bit cell questions, the questions would be like this. I'll show you next one. If intensity doubles, what is the change in decibels? If intensity becomes 10 times, what is the change in decibels? They would ask something of that sort.
So when do we use the gamma RT formula? When do we use this?
Gamma RT, which one?
The V sound wala.
Array, V sound, this is even more, if you ask, this is a more powerful formula.
Okay.
Because gamma RTM you define for gases, na?
Achha, right.
What if the sound travels in water or what if sound travels in a steel pipe?
Okay.
So this was a more powerful formula, and that bulk modulus is different for different gas processes. So that gamma RTBM is specifically for ideal gas, basically sound in a gas.
Right.
But this is a more general one. Now, in this, the questions would be like this.
In air, so we can use the gamma RT one also, right? For the
Where?
For air in the previous thing, we can use the gamma RT wala formula.
You need to give more data, na, temperature and all that stuff.
Right,
So
but you can.
we did that one question, kiya na? Your temperature varying with this thing, position.
Yeah.
Yeah,
Okay.
so we did that only.
Yeah.
Now see if intensity doubles. Now, if I just ask you like this, let's say when you hear that the intensity went from 50 decibels to 100 decibels, you know how much intensity changed? Let me ask this way. Let's say pH scale, if pH goes from 6 to pH 3, how strong is the acid? It's not double, it's 1,000 times. Getting it? So log scales are little deceptive. You have to be careful. So the new decibels would be 10 log 2i by I naught. This comes out to be 10 log 2 plus 10 log I by I naught, which is the old decibel. So beta nu minus the old decibels the difference would be 10 log 2, which is approximately 3 decibels. So for every 3 decibels, you can say on an average, right, this thing just doubles up. Same thing, if you make intensity 10 times, this will be mostly a bits at CT level question. Yesterday was the last day for the bits, second attempt. I think at least two of your seniors bumped up this course. One guy went from 263 to 329. One guy went from 310 say 331. And this would be 10 log 10 plus, that's a beta old. So the difference in decibels would be 10. That means for every 10 decibels, intensity becomes 10 times. So example, if you say the intensity goes from 50 decibels to 100 decibels, if here the intensity is I, here the intensity is 10 power 5 I, it's 1 lakh times. It's just didn't become double. So there, that's the intensity thing in decibels. Have a look at this. Clear? Let's see our question. So let's say we have a point source here. Meaning the waves are traveling in concentric spheres. And we have a line source here. Basically think of, electric field, equipotential. So here the waves are traveling in cylindrical, coaxial cylinders. So if there are 2 points here, A, and if there's a point here, B, let's say if this distance is RA, and if this distance is RB, if RB by RA is 2, find the difference in decibels between A and B. So you got a point source there and it is releasing sound. And here the point source is there in a line source. Basically here sound travels in spherical shells. It's called a wavefront. We'll see that in wave optics.
So can you please show the formula again for one?
We didn't write the formula.
No,
10 log I by I naught.
Yeah, thank you, sir.
Again, we're talking about an infinite line source. Find the difference in decibels between A and B. Get it. Easy one. Let's see. RB by R है तो values दिया है ना. See, the catch is for point source. Remember what is intensity? Intensity is power by area where the power is passing through. By the area where the power is passing through. So for the first case, here the intensity I would be P by 4 pi R square. So I is proportional to 1 by R square. So IA by IB will be in the ratio of 1:4 for a point source. For a line source, intensity would be power by surface area is 2 pi RL. That will be proportional to 1 by R. So IA by IB will be half only. So when you take the difference in decibels, beta B minus beta A, this is simply 10 log intensity of B by I naught minus 10 log intensity of A by I naught. When you divide them, it becomes 10 log IB by IA. There you got the difference. Substitute and get the answers. One will be 10 log 3 and one will be 10 log 2 and 20 log 2. Clear? So the main catch is that for a cylindrical, the power will be only 2 pi RL. It is 1 by R function. For a point source, it will be a 1 by R square function. If you think about it, this is same thing like, charge KQ by R square field. For a line charge, what is the formula? 2K lambda by R. 1 by R function. The idea is the same. They look quite similar in that sense. Clear with this? So intensity is power by the surface area where it passes through. Clear, everyone? Are in the page. Next one. So decibels part is easy. So just remember that formula. Most people forget the formula or kuch nahi hai. Either you forget the 10 there or you forgot that I naught ka value. I naught is 10 power minus 12. Next thing. Organ pipes. Stationary waves in sound. This experiment, right, you must have seen in the lab also. But first, let's see how this works. So whenever you take these organ pipes, right, are nothing but, thin pipes. So we have two types in them. One is an open. So in an open pipe, meaning both the sides, when you take it as open, let's try to understand. This is your open end. This is your open end. So the first thing, the particles at the open end. So if there is any particle there exactly the open end, it is free to move. It is not bounded. Are free to move. Basically, it's like a free end. Therefore, the open end is a displacement antinode. Now you have to be careful here because you can study sound waves in terms of displacement and pressure. Things get a little messed up. We didn't have this confusion in case of our strings. So this point can be a displacement antinode. So if you study in terms of displacement, the open end is a antinode. But same thing, the open end is exposed to atmosphere. So the pressure remains almost constant. Because if you want to change the pressure there, you have to change the entire atmosphere pressure. Therefore, it's a pressure node. So, if someone asks you what is an open end, the first question you should ask is, are you talking about pressure or are you talking about displacement? Generally, people talk about pressure, but you have to be careful. So the same thing can be an antinode or a node depending on which property you're studying. And we have seen last time also that displacement and the pressure were out of phase by 90 degrees. I mean, when this guy is maximum, that is minimum, vice versa. So that is what is happening there. So we prefer to study in terms of pressure. We prefer, but there is nothing stopping you from studying in terms of displacement. So questions can be framed. So in that sense, this guy is exactly like this question now. Sonometer. Except for the shape, mathematically, you'll not find any difference between them. So this is a node, this is a node. So we have both the sides nodes. So an open tube behaves like a string which is fixed at both the ends. Everything you derived there is valid here. Only thing there, the speed of the wave is root t by mu. यहाँ पे speed will be root gamma RT by m. And everything else will look same. Have a look at this. So if you take a pipe, both sides open, you'll see both sides open. Yeah, next thing. What if you have an open and a closed pipe?
So just 1 second.
Yeah.
When you said it's a pressure node, you're implying that the pressure like at the open
At the
ends.
point does not change. हाँ.
No, but like,
नोड
is
का
it
मतलब क्या
minimum?
था?
Is it minimum?
अरे minimum मतलब क्या होता है?
Like,
I'll punch you, you forgot last class, you didn't listen or you didn't revise. Pressure में what happens when the sound travels? There is a
like
pressure
minus
P
20 plus
naught.
20, yeah.
हाँ, मतलब नोड मतलब क्या? वो -20 +20 नहीं होगा. It is always P naught only.
So like inside it can be like anything lower.
हाँ. Just like string ना. अभी देखो ना. What is the displacement of this point? 0. It doesn't change, right?
Yeah, right.
Same thing. So pressure negative नहीं, pressure 0 नहीं. Pressure is this thing, what do you call it? The delta P is not changing.
Okay.
ठीक है?
Yeah.
And then open and a closed thing. So in this case, we have an open end. So this to we discussed already. So open end behaves the same way. Here there is a closed end. Now in a closed end, the particles, right, is fixed. So this guy behaves like this, a free end. So the particles at the closed end are fixed. Meaning if you take a particle on the container, it is not free to move. Therefore, it is a displacement node, but it is a pressure antinode. If you study in terms of displacement, that's a node. If you study in terms of this, it's a pressure antinode. Because it's a closed end, what will happen? The wave will overlap with itself, so the pressure doubles up. Clear? So this is your pressure antinode. There. Now we got similarities between this and that. Now let's see how sound waves form on this thing. How stationary waves form in this. So this is what we do in this experiment. Let's take an open. So we take an open pipe. Now remember, the other side is acting like a pressure node, means it is like a wall. So we take a tuning fork, and when we send sound waves, this is the incident sound. Since the other side is acting like a node, it's like a fixed end for sound. Meaning reason is this, I'll tell you what happens. If a compression goes to the open end, what will happen? You're going with high pressure, so the gas will just leak out. So you get a low pressure region. If a low pressure, a rarefaction comes here, the air from outside will push through, you'll get a compression. You're getting, if you get a tightly packed molecules to the edge here, the moment they enter the edge, because this pressure is more than outside, the gas will leak out. The pressure drops down. If a low pressure region, rarefaction comes there, the gas from outside will enter, so the pressure bumps up. So it's actually acting like a reflection. When a compression comes, you get a rarefaction. When you get a rarefaction, you get a compression. So this would be your reflected sound. So basically for pressure, it is acting like a fixed end. So the same story there. So incident wave and the reflected wave will overlap. And at some points they cancel out, at some points they add up. So if I write this thing delta P incident, delta P max sine kx minus omega t, delta P reflected will be delta P max sine kx plus omega t. You can take plus pi also, it doesn't matter. And then when you add them, the resultant, you end up with 2 times delta P max sine kx cos omega t. This is your general equation. You can see the resemblance. You can see the resemblance. Y is equal to 2a sine kx cos omega t. So, like I said, simply you're replacing delta P max with a, and everything starts looking similar. And the more general equation. So, if any book or somewhere in any question, you see something else, don't get scared. This is not the general one. So, delta P would be 2 delta P max sine kx plus phi 1. This is a most general form, which we have done in standing waves. Exactly same thing. See, Max doesn't care you're talking about sound or you're talking about a wave on a string. As long as the mathematical form looks same, it will behave the same way. That's your general equation, but we will use that sine kx cos omega t. We are used to that for all problems. Means we are choosing the node as an origin and the particles at extreme position at t is equal to 0. So this term here is called pressure amplitude. Is 2 times delta P max sine kx. Let's see what it means. And be careful, tuning fork, you have to keep it this way. If you keep the tuning fork like this, horizontally, sound will go this way. Sound won't enter. A CT question tha. How should the tuning fork be placed on top of it? Clear? And you can look at this thing. This thing is looking like this guy, the sonometer. Now we can take the possibilities. If you take the first possibility, so again the main story is what? The edges should be pressure nodes. In the middle, it could be anything you want. So the first possibility, this is a pressure node. This is a pressure node. The first possibility is you'll get one single loop. Let's try to understand what is the meaning of that loop later on. But for now, let's see the similarity. This is L. The distance between 2 points is lambda by 2. That is all valid. Lambda is equal to 2L. So the first frequency F1 will be V by 2L. Exactly same formula if you observe there. First harmonic of fundamental frequency. Only difference is speed of sound is gamma RT by m, and that speed is root T by mu. That's what it said. If you know that waves on a string, this thing becomes quite easy, except you just have to understand the pressure and displacement mode. Same thing, if you take the second possibility, now there'll be two loops. This we know is equal to 2 times lambda by 2. So we get the frequency F2 will be 2 times V by 2L or 2F1. Second harmonic or first overtone. Now we can keep doing this. So your general formula will be Fn is equal to Nv by 2L. V is equal to root over gamma RT by molecular weight in kgs. N is your harmonics. This is your formula for standing waves in an organ pipe. Turn back here. Please have a look at this. I hope you can see the similarities with this. Now that this doesn't feel that weird. No, let's see what does this mean actually. Now remember, in case of stationary waves, that loop indicated the different positions of the string. But here, what does this loop indicate exactly? Can I turn the page? Turn the page. So this loop indicates this is actually a graph. You're plotting a graph between delta P versus X. And what you're drawing here is the pressure. So when you say, okay, I'm just taking the fundamental one. So at a distance X from here, at this point, the pressure is delta P is 2 delta P max sine Kx. So when the wave is passing through inside, this is the pressure at every point ka graph. So at the center here, the antinode, the pressure is 2 times delta P max. So this graph actually indicates this thing is actually the pressure. This represents a graph. So these are not different positions of the string. There's no string here. This represents a graph of delta P versus X. So how can we visualize this? Think of like this. So that means at that point the pressure is 2 delta P max. Again, remember there's a change in pressure. Matlab P naught plus this thing is there. We are not talking about that P naught. That's a base value. It is P naught plus something more. Now the meaning of this is, imagine I make a hole here. And if I make a hole here, small hole, right? Since the pressure here is more, what will happen? The gas will come out with more force. And here the gas will come with less force. Now, if you take suppose if I'm filling this with a butane gas and if you put fire, then what will happen? I should see small fire here, big fire here, big fire here, big fire here, and small fire here, small fire. You will see the fire like this thing now. So using this concept, you can people actually use this in pyrotechnics. When you go to any big rock show or anything, right? They program the whole thing, the gas and everything is connected with this wave generator. And whenever the guy is playing the instrument and that sound forms the waves and you get a blast. And it feels like as if, the fire is dancing to your music. Let's see how it would have looked. Let's take a simple case. Where are you here? No, not this one, this one. This is a simple thing.
Classic physics experiment called the Rubens tube. Now, I really want to
So this experiment, right, is called Rubens tube. We don't have it. We don't use this in the labs and all. India mein to chance hi nahi hai. Students will blast the cylinder or someone will steal the cylinder. So
down, but it involves open flames, and some people have issues with open flames. So what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to propane. So let's up and see what it does.
So what he did, he took a 1 or 2 meters so long pipe, metal pipe, and he made holes every half-inch. He made a small holes. One side you kept a speaker. You can see the left side, there's a wire and all hanging. That's a speaker. So to send sound waves inside. The right side, you sealed it and you're releasing butane gas. So the right side is acting like a fixed end. So the sound is inside reflecting. So at a particular frequency, again, you'll never get standing waves at whatever frequency you want. Happens at a particular frequency. There.
Right.
Now there is no sound, nothing. So there's no sound, nothing. So if you can see all are same amplitude, right? All are same height because pressure is same. It is all at same height.
A little bit of oscillation from the vibrations in the hose. Let's throw some sound in there, see what happens. Let's start with a 449 hertz frequency.
Can you see the sine wave? That's the fourth harmonic. Dikha sine? It's bumping up and bumping down. Now you can't see sound, but you can see the flame.
As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compression here and here. The lower here allows more escape into that, making the sound. Now
if you change the frequency, you can see all frequencies don't come. Sixth harmonic.
Each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck?
This is what I was saying.
Now we have real life sound visualization with fire.
So that is what you would see. I had one more, I guess. Where is this? The same thing. I had a 2D Rubens tube. Where are you? I think this guy, I guess. This is more neat actually. Rubens tube, where are you? Somewhere here. I think I lost it, I guess. With the tuning for Kunsu. I'll find that. I'll post it in the group. That's actually 2D. That looks more nice, actually. I didn't have it. Okay. But I hope you got the idea now. So we can't see sound, but we can see the flames. All clear with this concept now? Now we know what the graph means. Clear? Now you can take it further. When we can do a, remember the free end ka thing, that also we can do open, closed. Can I turn the page? So remember this delta px, that loop which you are representing here is not the position, but it is actually the pressure which is changing with x. Now if you take a open closed pipe, again, all musical instruments, for example, flute is an organ pipe. Flute, tabla, all these are organ pipes. If you see the flute now, how does it look? You have a flute here and we have holes here. So by closing different holes, you're creating different lengths. So every musical instrument is either a sonometer or this organ pipe. Yeah, but flute will burn down. So if you make Rubens tube out of flute, you should take a metal thing. And where will you get gas and all? घर का gas cylinder लगा दोगे क्या? Don't do such things. Don't play with gas. They're very difficult to handle. Trusting mom and dad तो बड़ा fight हो जाएगा चप्पल से. And after that, I will get into the news next day. Physics teacher teaching students how to become terrorists. Headline जैसे ही आएगा. Suspected terrorist teaching students. Newspaper में क्या है ना, कुछ भी डालना है उनको. Innocent student got brainwashed to make bombs in the house. देख कितना articles है literally. So please don't try this at home. Just watch the video. Be happy. कुछ करना है. Once you go there, you can make your labs in IITs and all. You can make it under supervision. So this is a node. No, this is your anti-node. So this is your first possibility, open, closed. So in this case, we get the length L is lambda by 4. Same formula, we get frequency, F is equal to V by lambda is V by 4L. This is your first harmonic or fundamental frequency. What is the second possibility? The second possibility will be one full loop, and the last thing should always be an half loop. So 3 lambda by 4 is equal to L. So we'll get F3 is equal to 3V by 4L. Again, the even harmonics are missing. So this is your third harmonic and first overtone. Like I said, you can see a lot of similarities, exactly same thing. So we can write a general formula here. Fn is equal to 2n plus 1 V by 4L, where n is the overtones. And remember, in this case, even harmonics are missing. You can see the resemblance. This guy is exactly like this, a free end. Free end oscillations. There. Have a look at this. The closed end at this point is fixed now, right? That particle can't move, right? It has to be a displacement node. What is the meaning of a node? It won't move. So it's a displacement node, it is a pressure antinode. And think of like this: when a wave is traveling, you're sending refractions and compressions. What are you exactly sending? You're sending molecules, right, which are compressing and coming. Now, when this thing comes and hits here, dekho kya hoga? Let's say this is molecule 1, 2, 3, 4. When the molecule hits here, this is 4, 3, 2, 1, right? Now, after hitting and overlapping, dekho kya hoga? This becomes 4, this becomes 3, this becomes 2, and this becomes 1, right? So 1 and 2 are traveling like this, 4 and 3 are coming like this. So in the same space, we have double the number of molecules. So pressure became double, isn't it? Next thing. Now in this thing, there is something called an end correction. The thing is, even though we say the open end is a pressure thing, but the problem is when the compression comes or rarefaction comes, it pushes the atmosphere slightly outside. So the pressure node exactly does not form on the open end. The pressure node forms slightly outside the open end. That means the node instead of here, we take the node here. So this distance here is called end correction, meaning for the whole wave, the length of the pipe is not L, but it is actually L plus 2V. So the length of the pipe length will become L plus 2V. So your formula will become F is equal to NV by 2L. L ka place will get L plus 2V. The E ka value is given by 0.6 R or 0.3 D, where R is the radius of the pipe or D is the diameter. When do you know you have to use this? If they give you the radius of the pipe, that is a big hint that he's talking about an end correction. Same thing, if you take an open and a closed end, in this case, there's only one open end. So this is E and this is L. So here the formula becomes 2N plus 1 V by 4L. L ka place will get L plus E. So exactly same thing, only thing wherever there is an L, yeah, there is no problem as such, but you took the wrong length, isn't it? Now this whole length is lambda by 2 and this whole length is lambda by 2, isn't it? But previously what we were doing while deriving, you took lambda by 4 is equal to L, but in reality, lambda by 4 is L plus C. That's it. So we have to take care of the small correction. This is called end correction. Clear, everyone? Next thing. So this is the theory of the organ pipes. Now on this, based on this, we have two experiments. Easy one, meaning the basic concept, if you know the experiments are easy. The first one is resonance column method, which you have seen in the lab. If you have done it in the lab, you will do this. Resonance column. Basically, this is an experiment to find the speed of sound. You should know the diagram and everything, because simply sometimes question will say in resonance column this is happening. And if you don't know how the diagram, what is a diagram, you'll be stuck. Yeah, this is the proper setup. Right? Let me show it in a more simpler version. So the simplistically, this thing would look like this. We got a pipe here. So at the bottom here, it is connected to a something like this. To the right here, we have a scale. So this thing is a movable funnel. You can move it up and down. Getting it? So the catch here is, if the funnel, if I keep the water till here, we know from fluid mechanics, we can be sure the water level is also same here, isn't it? Now you can't look into the the pipe and see what is the water level. We need something to find the water level inside this. So this funnel will tell you that whatever is the funnel level, that is the water level inside. So by moving the water level, we can change the water inside this thing, right? Which can be adjusted to change the length of water column inside. There on the left hand, you can see the diagram is more neat, but I'm just giving you a rough thing. Now the idea here is, I'm going to take a tuning fork and we're going to produce sounds. So the sound will go like this, it will hit the water and will get reflected back. So this is behaving like an open end, and this surface is behaving like a closed end. Basically, you created an open closed end ka pipe. So by changing the water level, you're changing the length of the column. Now in this thing, right? So what we do, we take a tuning fork, we keep it, and we keep adjusting the water level. And when you keep adjusting the water level, suddenly at some point you'll hear a sound like boom, karke, the whole thing vibrates. You get that boom sound karke. So that means the standing waves are formed. They'll simply say the entire tube resonates. When the waves are overlapping properly, you get this thing. So using this setup, we need to find the speed of sound. So the only thing in your hand is, the frequency of the tuning fork. You can change the length of the water column. Using these two things, we have to find the speed of sound. Is the setup clear, everyone? So this is what we do. So first, you fill up the tube completely. Initially, resonance column is fully filled. And you start slowly decreasing the water level. When you keep doing this, first time you'll get that boom sound. Let the liquid level be like this. So this length L1 will be the length of the air column. Now be careful, in the question, are they giving length of air column or water column? Which you can calculate, the length of the pipe. So length of the pipe minus water column will give you this. That means we know the wave will form slightly outside. Remember, this length is L1 and this is your end correction. So from here, we get lambda by 4 is equal to L1 plus E. Then you continue to decrease the water level. Then the sound goes off. Then again, you'll hear that sound. Now we are sure the next overtone has formed. Now this length of the air column be L2. Remember, air column length is only from the top. Now we get 3 lambda by 4 is equal to L2 plus E. Now we subtract L2 minus L1, that will give you lambda by 2. So even if they give you water column, right, the difference in length in water column is always lambda by 2. That is the distance between two loops or two nodes. So from here we calculated lambda. Even though you have end correction problem, nahi hai, cancel ho jayega. And the speed of sound is frequency into lambda. Frequency of tuning fork I know. Now the lambda also I calculated. So basically this experiment is used to find the lambda. And done, we got the speed of sound. Simple experiment. That you should know how it is working and all. They'll suddenly say resonance column, so you won't have an idea what he's talking about. So end corrections won't create any problem because they would cancel out. Have a look at this. Clear, everyone? So this is one experiment, resonance column. Can I go ahead? Did you guys do this in the lab? Dekha hoga na? Some of you at least must have done this. They didn't do yet. Did it.
Yes, sir.
They'll give you a steel glass with water. I either did that way only. No, you guys did more classy way, I guess.
So they didn't give the funnel and all, but they gave some pipe. So समझ में नहीं आया वो teacher ही मतलब like she was manipulating it and was like.
हाँ वो तो है ना lab में तो we तो used to give 50 rupees. We used to go to the lab, give 50 rupees and done. We used to get 30 out of 30 marks. बहुत easy था ना. Next thing. Kunst tube. Now Kunst tube, right? We saw that Rubens tube, which is more cool. Now, but we don't want to use fire and all, so we use something else. Again, Kunst tube is also an experiment to find speed of sound. Be careful with this wordings, right? Concept kuch bada nahi hai, but they will say in a Kunst tube, and you'll think what the hell it is. So what is this Kunst tube? We fix one side. Again, I'm drawing a very simplistic thing for concept wise. And on this side, we have a movable piston. So we take some powder here and we put it inside. We sprinkle some powder. Now you use some source or something, tuning fork, like, you keep a speaker and you generate waves. Now when standing waves form on it, now think about it. The powder at the displacement antinode, we are talking about the displacement now. Powder at displacement antinode. Understand what is antinode? Particles at that point have maximum displacement. So if you keep powder at the antinode, it's going to fly. And if the powder flies, what will happen? It will start going away from there. Flies away. And the accumulates at the node. Because the powder at the nodes will never move, eventually the nodes will start collecting more and more powder. So after some time, the diagram would start looking like this. You will see heaps of powder like this. You will start seeing this powder. The powders will start accumulating at this point. That means these are what? Antinodes or nodes? That means what is the distance between them? Lambda by 2, na? So I can measure the distance between the two heaps. Now these are what? Antinode and antinode, isn't it? What is the distance between two antinodes? Lambda by 2. So I can find out how many heaps will form. I know the length of this thing. From there I can find the lambda, or I can find the distance between two heaps. You can do that however you want. एक बार वो हो गया, then you're done story. So V is equal to F into lambda. So if you see now the whole question, right, all the experiments are mainly one thing. You already know the frequency, somehow find the wavelength. If you can somehow find the wavelength, which is actually the distance between nodes or antinodes, and then multiply F into lambda, you'll get the speed of sound. This is called Kunz tube. The setup, right, the actual thing would have looked like this. This is a more beautiful diagram. They take a pretty long tube. This is how the setup would look. Clear with this? Is the concept clear? Idea was pretty simple, right? This thing, where are you? Kunz tube. Here. So this guy is using thermocol. Can see the middle part bumped up. The first harmonic. That's a 119 hertz. You can see the center main node, antinode, and the edges have slimmed down. If you double the frequency, volume decrease करते हैं. There you can see two loops. So that's what is happening. Wherever there's an antinode, the thermocol, those things are flying more. दिख रहे हैं ना clearly sine wave. 3 loops, third harmonic. Only third harmonic is giving you headache, Utsa. We can go to 9,000 hertz. It's a pagal ho jaoge. That is 357 hertz. Now you can even create, half loop and all. We can move this thing. This is a 1.5 harmonic actually. The left hand you can see. So yeah, that's the Kunz tube. All clear with this? I hope conceptually everything is clear. Great. Let's see some questions. This thing that we already did it. Let's get this. This is a fundamental frequency. This is also fundamental frequency. This is all a fundamental frequency. Get this question. Within a single loop, why there is a gap between the powder particles? Oh, actually, particles nahi hai. I think those things, it is not thermocol also. It is just some kind of paper kind of thing. So wherever there is more pressure, the paper is being pushed up more. Individually, particles nahi hai. I think the whole setup, I feel it is something like loose paper here, loose paper here, loose paper here, loose paper here. Wherever this antinote, this paper was going up, this paper was going down, this paper is coming down. तो इसीलिए वो गैप था. It is not a powder or something. Powder नहीं था, thermocol नहीं था वो. Something else it was. So let's get this 36 and 37. When they say word open pipe, na, he's talking about open. So exam they'll say open pipe only. It means open. Closed pipe meaning open closed. If it is closed on both the sides, you'll mention specifically. So there are certain things you have to be careful with the words. Let's go. So basically, a resonance column is nothing but an open closed. Let's try this thing. क्या होगा? It's a headache आ गया. Happens. And with that frequency generator, you can actually harass dogs also in your apartment if you want to take revenge. Or your sister or brother when they're sleeping. You can take the phone, put it under the pillow, 9,000 hertz. What is science for? To take revenge. Nee? And agar time permits to do some good things. But good things, I think people have done enough anyway with science. Let's do this thing. Kya tha first one? An open pipe resonates with frequency F1. So just let's draw a small diagram. Don't try to, at least I don't rely on formulas. I don't remember them. So you said it's a fundamental one. Right? And so this thing is what? So lambda by 4, you can derive them, or you can say F1 is equal to the open, so V by 2L1. The second pipe is an open closed. Lambda by 4 is equal to L, so we can derive it anyway if you want. So F2 will be V by 4L2. Now when I combine these two, you created a pipe of length L1 plus L2. This also is fundamental, so you'll get only one loop here. So this frequency F will be V by 4 L1 plus L2. So get L1 from here, V by 2F1. Get L2 from here, V by 4F2, and substitute here. So V by 4, L1 is V by 2F1 plus V by 4F2. V gets cancelled. This will be 2 by F1 plus 1 by F2. F1, F2 by 2F2 plus F1. Yeah, first option. बस यही करना था. Check it out. अरे fourth option तो chance ही नहीं है. God, dimensions match नहीं हो रहा है. $37. Keep going. So in a resonance column experiment, the first and second resonance are obtained at lengths L1 and L2. The third resonance will be obtained at. Okay. Try, I'll give you another 30 seconds. Draw a small resonance column. That will be easiest way to see. The first one is this, second one is this, third one is this. This is the first one, so this length would be L1. This is L1 plus E, and don't forget the end correction. This would be like this. This is L2 plus E. This is the second one. This would be like this. This is L3 plus E. Now, one thing you can clearly notice here, if you take L2 plus E minus L1 plus E, the difference should be lambda by 2. But this is also equal to L3 plus E minus L2 plus C. So if you remember this thing, right? So one length to one length, the difference is always lambda by 2. You get L2 minus L1 is equal to L3 minus L2. So we get L3 is equal to 2 L2 minus L1. Easy. So whenever they say the reading is L1, L2, L3, the difference is always what you call this thing, lambda by 2. Yeah, I thought draw. It is better to, feel stupid and get +4 than, feel genius and get a -1. So that's a choice. What is more important? This is something you will learn in life as you go ahead. Will you take it on your ego and fight with your friend, or you just go and say sorry even though it is your mistake? Second is always a good option. Say sorry, make him feel guilty, and later after 3 days punch him right and left. It works. Clear? I never resorted to violence. I used to just go and change their computer ka RAMs. I used to replace their 512 MB RAM with 120 MB RAM. Their computer used to be slow. For 4 days, he used to suffer. He used to go and cry. Everyone, अरे मेरे computer का कुछ हो गया. I used to say it is virus. Infect हो गया. पूरा format करना पड़ेगा. We used to make it format. And then after 4 days, put that thing under the pillow. If it doesn't break it, he will realize. So he used to get his RAM back. And that's what more can you do? Next thing. We are a very strict followers of Gandhiji. Violence does not solve anything. Next one. Let's go. These all are like, straightforward bits and mains level questions. Kuch itna bada, there's nothing to ask also. But if you got these things, the tough ones are the same thing. अभी next time करने के लिए अभी कोई है ही नहीं रे friends. Everyone is busy everywhere. बोल रहा हूँ ना अभी देखो I passed out almost 14 years back and I still remember so much. I'm telling you, the 4 years that's the best time of your life. Because you have meaning you just come out of the room and there are 200 idiots like you in the hostel running around. And you will not find anything like that anywhere. Meaning imagine, right, evening, night 10, 11 o'clock, power went off for 10 minutes, right? And the most common activity we used to do, when power goes off, we come out and shout. Just like that, randomly. So generally I used to start. I used to come out and start shouting. The guy in front of my room, he used to come and shout. Competition, who will shout loud. And to support me, my friends from the other rooms used to come and shout. And shouting se thoda dukta hai na. So what I used to do, right? Again, you have to use your head. These water bottles used to be there, na, big ones. I used to bring them both and used to beat them both. Badam, dum, dum, karke. That used to make even more sound. So the other team used to get pissed off. They used to make more sound. So our entire hostel is shouting. In 5 minutes, entire hostel is shouting. Imagine 200 people shouting like mad. So because our hostel is shouting, the other hostel gets offended and think we are fighting with them. The other hostel starts shouting. In around 10 to 15 minutes, there are 17 boys hostels in IIT Madras. Everyone is shouting. No one knows why. And the people from outside the campus are thinking, "Andar kya ho gaya? Pagal loge." Initially, they used to get scared, but after that, they termed as, pagal loge andar. So, and power comes and people just vanish. People do all crazy things. I used to think we are weird. My juniors are even more hopeless. These people, right? One day power went off. These people, right? They brought all this paper, broken wood, everything. Hostel ka beech mein fire dal diya. And around, hoo, ha, hoo, ha, hoo, ha. They were running around the fire. They were playing tribal dance. It was interesting. I was telling my friend, हम भी जाते अच्छा लग रहा है. Then he said, next day inquiry होगा, सबको पकड़ लेंगे, तू चुपचाप रहो. So I kept quiet, and next day there was an inquiry. You're not supposed to burn anything in the hostels like that. Juniors को right and left quoting मिला. I think they got fined some 5,000 rupees, but ठीक है. Anyways, let's get back to this. People do crazy stuff. You will find really weird guys, right? One of my friend, na, he's like, अरे मैं library जा रहा हूँ पढ़ने के लिए. He went. I also went to see him. He's there busy on the fourth floor, air conditioned. He has big books on thermodynamics and everything, and he's sleeping on them like a pillow. Then I said, bloody to kar kya rahe ho exactly? The same thing on student also told me, but this is the first time I heard. So then I said, to kar kya rahe ho? He said, these books are there. They has a highest concentration of knowledge. My head is there. The concentration of knowledge is low. Due to diffusion, knowledge flows from high concentration to low concentration. So I'm trying this hypothesis by sleeping करके he slept again. अभी वही होता है when you know बहुत ज़्यादा पढ़ाई होते हैं तो your jokes also start looking like science. That was a diffusion joke. क्या करेंगे अभी? चल, let's finish all the 38. Study, put up fight. Trust me, it is really worth it. You will find so many idiots. Na, I don't know about the education, but the kind of people you'll meet, na, it's a game changer for you. So if you ask me, sir, IIT क्यों जाना है? This is what I tell everyone, to get pretty good friends. You will not get those kind of idiots anywhere. So an open pipe is in resonance in second harmonic. Now one end of is closed and frequency is increased to F2 such the resonance occur in nth harmonic. Choose the correct option. So an open pipe is in resonance with the second harmonic. So open pipe, na? Second harmonic is two loops. So this F1 is nothing but V by L. So basically this is 2 lambda by 2 is equal to L. Neglect the end correction. So we got F1 is equal to V by L. Now he's saying the frequency increase of resonance again occurs in the nth harmonic. Now you closed it. So this guy, the frequency will be now NV by 4L. Okay? Now this N is odd number. So this N should be 1, 2, 1, 1, 3, 5, and so on. Basically, N is an odd number. And this frequency is F2. So take V by L and substitute there. So we get F2 is equal to N by 4 V by L. V by L and F1. So, and N should be odd number. So you can just check it out. So answer can be F2 can be F1 by 4 or 3F1 by 4 or 5F1 by 4 and so on. And see which option matches with this. I think I can take N is 3. First option, if I put N is equal to 3, so that will be 3V by 4L. F2 will be 3F1 by 4. First option match हो रहा है. N is equal to 5. C option भी match हो रहा है. A and C, ना? Two answers are there. Make sense? Next thing, 39. Give it a try, everyone. Any doubts on this? Please ask me. Like we are just playing with the two formulas there. Open pipe, open closed. Closed organ pipe, matlab open and closed. And an open organ pipe. So two different things are there. Again, density rho 1, rho 2, compressibility. I hope you remember what is compressibility. 1 by bulk modulus. Compressibility is 1 by bulk modulus. Both the pipes are vibrating in first overtone. The length of the open organ pipe is, it is just all formula manipulation. There is nothing there. Try, you got 2 minutes. closed organ pipe first overtone मतलब third harmonic था. So this guy is 3V by 4L1. Now be careful, since the density is different, speeds are different. The wave speed is not same in both. The first overtone is your second harmonic. Here the frequency will be 2V2 by 2L. This length I don't know. So if I equate them, you end up with 3V1 by 4L is V2 by L2. So I get L2 is equal to V2, 4V2 by 3V1 into L. And we know V is nothing but root over bulk modulus per rho. Yeah, the bulk modulus is the compressibility. This is 1 by, okay, compressibility is same, so bulk modulus is also same. This would be 4 by 3 root over B by rho 2. This is B by rho 1 into L. 4 by 3 root over rho 1 by rho 2 into L is L2. Second option. No, first option. Easy? There basically we have to use the speed of sound formula here. Clear? Take a break, come back with 7
So can
Any
you
doubt
show
so far?
the previous slide for 1 second? I'll just take a
This
screenshot.
one?
No, before
one.
that, I got disconnected. So just
Hmm,
the Kunst-tube, that one.
पूरा disconnect हो गया क्या?
Yeah, I don't know. My laptop's not working properly today. Okay, thank you, sir.
Chalo, come back in 10 minutes. Chalo, comes on everyone. Chalo, let's get these 3 questions. The main thing in these kind of questions, right, is getting used to that formula and that pipes and all. You got the hang of it, you'll be able to handle. Let's get them. Give it a try. Got 4 minutes. Okay. First was easy. A tube of certain diameter and the length 48. Now, the moment you hear the word diameter, he's talking about end correction. Is open at both the ends. You can clearly see here lambda is C by F, which is turning out to be 1 meter. So distance between the loop nodes lambda by 2 is 50 centimeters. But you're saying the length of the pipe is only 48 centimeters. That means the first harmonic, this guy is 48 centimeters, the pipe, and 1 centimeter up and 1 centimeter down. So indirectly, he gave you the end correction E is equal to 1 centimeter, which is 0.3 times the diameter. That is 10 by 3 centimeters. 3.33. Clear? That was the idea there. The distance between the nodes should be 50 centimeters, but the pipe is only 48, meaning the nodes are formed slightly outside the end correction. Next one, keep going. Yeah, oh, yeah, because of the frequencies, people got headache. Yeah, people also left. This is good actually. I think medical students, if they don't study, can do something like this. What is the second one? A closed organ pipe of length L. The air in it vibrating in third overtone. Matlab 7th harmonic था वो. He's saying the amplitude at a distance L by 4. Amplitude, he's talking about distances. So this point is your displacement node. It's a pressure anti-node, but displacement node. This is displacement anti-node. So that means this guy, something like this. So this is your 4th overtone, 3rd overtone, or 7th harmonic. 7 half loops. That's what I'm saying. Don't get stuck with that formula. If you can draw and figure out, that is always best, safe. So indirectly, we have 7 times lambda by 4 is equal to L. So lambda is 4L by 7, or we can say K is 2 pi by lambda. 2 pi lambda is 4L into 7. 7 pi by 12. Here we can write the amplitude is 2a sine kx. But I think here the amplitude, maximum amplitude is given as a, so a sine kx. So you want at a distance L by 4 from the closed end. So you want somewhere here L by 14. So a sine k is 7 pi by 12 into L by 14. That becomes a by root 2. Clear? Since you're asking for displacement, I'll keep everything in displacement. I won't use pressure here. This thing actually becomes like a string only. Keep going. 42. Now we are comparing sonometer with organ pipe. Any answers? Try. Leave a minute or two.
So the answer was coming negative. I tried 42.
Yeah. First overtone of closed pipe. क्या लिया तूने? Third harmonic.
Yes, sir. I took
A
V by 2L
frequency
is
of a
equal
stretched
to,
wire with uniform certain length in resonance with the fundamental frequency of a closed tube. Okay.
so,
So,
8 minutes, I took it wrong.
so stretched uniform wire a certain length is in resonance with the fundamental frequency of closed tube. Okay. So fundamental frequency of closed tube is V by 4L. So basically, its frequencies will be, and then he's saying it goes with first order. Okay, so let this frequency be F, 3F, 5F is the frequencies we get. So the first one, F is equal to, now he said simply resonance with the fundamental frequency. He never said string is in which harmonic. So it is N by 2L root over T by mu. This much I know. Then he said when you decrease it by 0.5, it oscillates again. So again, I am assuming there is nothing in the middle. So this is 3F. Will be again N by 2 into L minus 0.5 root
But
over T by
N1
mu.
and then into the more.
Yeah, we are assuming. So we have to assume वो तो I think harmonic same होना चाहिए. There's no other option right there. The harmonic should be same. Because नहीं तो actually वो दूसरा we need one more data point then. When you decrease the length of the string, assume still, I think you should have said it is a fundamental frequency only. So एक काम कर लेते हैं. That should have been given, but you can't solve if you don't take that. So we'll assume same harmonic. So then I think you can divide them. You'll end up with 1/3 equal to 1/2L L minus 0.5. Three L minus 1.5 is equal to L. L is equal to 75 centimeters. वो same लेना पड़ेगा, option नहीं है. Clear with this? But I hope at least you got the formulas. Any doubts on this? The direct, if you see, all it is formula based. Let's see one more. Going ahead. Going ahead. It's a paragraph. There, let's get this thing. There are 3 questions. It's a paragraph question. Let's get this. Then an organ pipe may be closed or open of 99 centimeters. Standing wave is set up. The longitudinal displacement, these are displacement, not pressure, is given. Using this information, get the first, second, third questions. Try, you got 3-4 minutes. Anyone not clear with the question? Anything confused? Ask.
So there was an equation दिए on the left side. What does that weird symbol in the start?
वो displacement है, instead of y he took something else. Basically already y coordinate use कर रहे हैं ना हम यहाँ पे.
Okay.
That is simply displacement. Call it epsilon, eta, whatever you want to call. Just some displacement और कुछ नहीं. Normally we use y, but यहाँ पे vertical तो y coordinate already used हो गया. Option open closed. That you can see. We can clearly see there. If you put, let's look at the equation there. That weird symbol, whatever it is. The equation is 0.1 mm cos 2 pi by 80 y plus 1 centimeter. This whole thing would be an amplitude cos 2 pi 400t. So this whole term is your amplitude. Now you can clearly see here at y is equal to -1, we are getting amplitude is max. Now remember, this is a displacement amplitude. That is, it's a displacement antinode and a pressure node. Pressure node meaning it is exposed to atmosphere, means it is a open end. And that 1 centimeter is an end correction. And if you take it y is equal to 99, we can see amplitude would be 0.1 cos 2 pi by 80 into 100. That is 0.1 cos pi by 2. Yeah, which is 0. It's a closed end. So it's a closed end open end. And from the pipe, you can clearly see this is the point which is forming at y is equal to -1. This is y is equal to 99 centimeters. So this point is your end correction 1 centimeter, which is 0.6 r. So the pipe is pi by 3 centimeters. And that's the first thing. So it's an open closed. What about the second part? Bulk modulus is given. So I know displacement, I'm asking for pressure. Okay. You need rho. नहीं, rho नहीं लगेगा. Which formula we have to use for the second one? Bulk modulus is equal to dP is equal to minus bulk modulus dou y by dou x. Hope you remember. So in this case, dP bulk modulus y ka place mein we have that weird symbol and x ka place mein we have y. So you have to do partial differentiation with respect to y. So time ka term won't change. Only the cos ka term will become sine. So there should be a sine ka term here. There are two options. Cos though should remain same 400. तो ये तो गया. So you can just eliminate the option. There's no need to solve. And we can also write that delta P max is BAK. So from there you can find the amplitude also. But I think this was easy to guess at least. This should become sine and this should be cos 400t. So this is gone. That is only option left. If you do BAK, you'll get that 125 also. The 65, assume end correction is given, estimate the number of moles. So yeah, this is the reason I found the radius. So this whole tube length is 99 centimeters. So from here we'll get the volume, which is pi r square L. Then I can use PV is equal to nRT. Pressure we can take almost same, even though it is slightly varying inside. Or you can actually use this concept. He said 22.4 liters is 1 mole. So you can use up this thing. 22.4 liter is 1 mole. Then pi r square L is how many moles? Unitary method, you'll get the answer. So that's the reason you need the end correction. You can figure out the number of moles inside. Do have a look at the question. Easy one, like I said, but you're playing around. What we did in stationary is on a string. If you got that idea, the similarities are same. Only thing is like the pressure and stuff, you have to be careful what you're talking about. Any doubts on this? Clear, everyone? That's the stationary waves on a sound waves. The next thing is beats. So what are these beats? Now, till now, in stationary waves, you are taking two waves of same amplitude, same frequency in the opposite direction. But let's say if you take two waves, slightly different frequency, first we'll see the mathematical approach, what it gives. That is important. So listen carefully. The derivation is important. Slightly different frequencies are superposed. We observe an increase and decrease in intensity of sound. So if you take the two equations, y1 is equal to a sine kx minus omega 1t, y2 is a sine kx minus omega t. Technically, even k will change, but we can approximate it. So basically, we are saying delta omega 1 minus omega t. This is the difference. Delta omega is much less than omega 1 and omega 2. Example, let's say f1 is 300 hertz, f2 is 301 hertz. The change in frequency is 1 hertz. It's quite small. So therefore, we can assume k1 is also almost equal to k2. Actually, the k should be different. Very small change we are taking. Now, if you add them, the y resultant, y1 plus y2, you end up with 2a sine kx minus omega 1 plus omega 2 by 2 t cos omega 1 minus omega 2 by t. So this can be written as 2a cos delta omega by t. That can be written as sine kx minus almost omega average, which is omega 1, omega 2 only. You got a pretty interesting equation here. Have a look at this. Next thing. Okay. Now look at this equation. So we got the y resultant is 2a sine cos delta omega by 2 time sine kx minus omega t. So what you got is a progressive wave whose amplitude is changing with time. In a stationary wave, amplitude was changing with position. This is an amplitude that changes with time. And this is your progressive wave. So now we got a progressive wave whose amplitude is varying with time. So if I try to plot this on a thing, let's see how it looks. First, let's draw a normal one. Then you can see the comparison. If I draw a sine kx minus omega t, remember I'm drawing yt graph. That means I'm looking at the one particle for all times. So if I keep x constant, what I will see is an SHM. So this is how it would look. It's a high frequency, so the waves will be pretty close. Now, when I try to hear this sound, what you'll hear is this. Even though it is changing, because the frequency is so high, your ears cannot differentiate. Let's say if you're hearing a 100 hertz signal, this is 100 times per second, your ear will think it's a constant sound. So high frequency. So anything more than 10 hertz we can't detect. Any frequency greater than 10 hertz will sound like a constant sound. It will be heard as constant. So human ears, right? We have a limit of 0.1 second. That is what happens when two of your friends are talking to you at the same time. You don't understand any of them because the sounds are coming one after another. Your brain doesn't know how to pick it up. Now, if I plot this guy, listen to this, and this is an important one. Two-way cos. So basically, it is the same wave, but now you have a time varying amplitude. So at t0, you have maximum. So you start from two-way. And as time passes, you decrease. Then again, you increase. Then again, you decrease. Then again, you increase. Then again, you decrease. So the amplitude is increasing and decreasing. So if I try to play this sound, what we'll hear? If I start from here, it is like, meaning it will go up and come down. It will go up and come down. So what you're hearing is the envelope, basically. You're not hearing each and every wave. What you're hearing is the envelope. So this difference, right, is called one beat. The difference, minimum to maximum to minimum is called one beat. Right. So this kind of wave, right, it's called a waveform. So it's a waveform of a beat frequency. So this is what is happening when you have two different slightly frequency. What you're hearing is this thing, the increase and decrease in intensity of the sound. So this equation would look like this. So the amplitude varies from two-way to zero. We are again talking about the same point now. Meaning if you just keep your ear at same position, you will hear the sound is going up and decreasing. So here we have an amplitude that changes with time. Let me show you how it would look. I need a multiple tone generator. Why am I not getting this? Oh man, this is one. This is not letting me generate multi-tone generator. Let's see, in the meantime, let me show you something else. I hope this is clear with the beats. So let me just complete this. So we can see this value is going up and bumping up. So this amplitude is 2a sine delta omega by 2t, sorry, cos. So the frequency would be omega by 2 pi. So omega ka place mein we have delta omega by 2 pi, which is omega 1 by 2 pi minus omega 2 by 2 pi into half, which is nothing but f1 minus f2 by 2. That means the frequency in one time period, this is called beat frequency, meaning the function ka periodicity is f1 minus f2 by 2, means in one time period we get 2 beats. Therefore, the number of beats, meaning in one time period of the wave, we get 2 beats. So in 1 second, will be 2 times number of beats per second, will be 2f, which is mod f1 minus f2. This is the formula. The result is nice, but the derivation is important. I'll show you later on why. So again, you have to be careful here. If the beat frequency exceeds 10, you can't differentiate. But machines can still detect. If number of beats is greater than 10, humans cannot distinguish. You'll think it's a constant sound. Clear with this? Now, when you play with the tuning fork, right? So if you take our tuning fork, if tuning fork is waxed, normally you take a candle and you rub the wax over it. So what are you doing? You're making it more heavier. The prongs, you're making them heavier. So frequency decreases. Basically, let's say if this is some 100 hertz, you take a candle and you put a lot of wax. Maybe the frequency will become 98 hertz, something like that. The tuning fork is filed. Meaning you must be knowing, right? When you polish your nails with that nail cutter ka thing, filing, you're making the prongs thinner, which we will not do normally because the tuning fork will be permanently damaged. The frequency increases. So this is a bad idea. So you can change the frequency of the tuning fork by making the prongs heavier or lighter. Frequency increases. Now I need this concept. Let's see why. But I hope everyone got the waveform part. I'm still searching for a frequency generator, but let's see. In the meantime, where are you? Content. I used to find it online. Bloody all funny videos, stupid videos I get. Things which I need, I don't get. Look at this. It's a good one. It's a good video. MIT ka. So keep things silent and listen. We can't listen to the sound of it. So here, what they did say, they took that box thing, and that is a tuning fork. That box is actually an open organ pipe. If you think about it, isn't it? That box is an open organ pipe. You're keeping a tuning fork. So when I hit this at a particular frequency, the standing waves will form inside. So when the standing waves form inside an open pipe, you'll hear a boom sound. So here already these people know the length, frequency, sub adjust kar liya. So things are already ready here. So we have a weight attachment. Now see first normally how it sounds. This is the sound I was saying. boom, so whenever standing waves form, right, this is a sound that you hear. Okay, now we have both the tuning forks. Now see what happens here. You're hitting the right one. Okay, now see the left one you didn't even touch. Now you can hear the sound. Fair enough, because you hit it. Look at this thing. You can hear also the sound. So what happened here is, when you kept them together, when you hit the right one, the waves from the right entered the left box. And the stationary waves formed on the left one also, and the tuning fork started vibrating. So this is what we call as resonance. If you have two systems of same frequency, and if you oscillate one, the other one also will start oscillating. Making sense? This phenomena is called resonance. Now you took both of them. He's going to keep a weight. Now the problem is the frequency change on the left side. Did the frequency increase or decrease? By putting a weight, it becomes more difficult to oscillate. The frequency decreased. Now the left frequency is less, right frequency is more. So this sound you can hear. Now look at the other one. Silence. There is no sound at all. Now, because the frequency is different in both the tuning forks, it is not resonating. Even though the waves entered, it is not forming a harmonic. The left thing is not working anymore. They're not in resonance. So if you mess up two systems with two different frequencies, and if you oscillate one of them, the other one won't react. So now we got two systems, two tuning forks with different frequency, and now see what happens. So you're playing only first one. Great. The other one is a different frequency. Can you hear the beats? If you see that again. So the right one has a different frequency, left one has slightly different frequency. So you have two sources with different frequency. That sound is up and down, it's going up and down. That is what we call as beats. This, in your phone, right, you can download an app called Online Tone Generator. In that, you can put 3 or 4 frequencies at the same time in the phone. So in that, if you keep one as 400 and one as 402, you can hear beats. Some reason I couldn't find it in the Chrome. Everything is showing Android app. Yeah, everyone is giving only one source. Why can't I get? I have 2 sources, I guess. I think this should work. Let's see. I'm not sure. So there we have 2 here, 500 and 503. So let's make this also 500. But he said left ear, right ear, na? So I think it won't work. This won't work. Maybe if I make this 502 now. I can hear. Dikh rahe beats? See, you are hearing actually. Let's make the frequency a little less because some people are getting irritated. Now see 300, you will hear constant. Sune dera constant? Okay, now I'll make this 300 and 301. That is 1 beat per second. Make this 302. That is 2 beats per second. If I make this 303, that is 3 beats per second. I can go for 308. That is 8 beats per second. Now, if I keep exceeding 315, now we are reaching our limit. Can see it almost feels like it is constant. Actually, there are 15 beats per second. If I go 325, you think it's a constant sound. We can't differentiate the beats, but there are 25 beats in that second. It's an online tone generator. You can just search online mein mil jayega website. But app mein to you can do that. App mein to even better, you can put 3 frequencies. So that way we can play around. So is everyone clear with the beats part? I hope the theory part was clear. Why you are getting beats? Two frequency तो मिल जाएगा. I couldn't search, I guess. There I got it anyway. Clear with this? Any doubts on this part? Great. So let's see one question. So we have a tuning fork here, FA, which is 500 hertz. We have a second tuning fork, FB, whose frequency I don't know. So initially, A and B produce 4 beats. Now when B is waxed, you took some wax and kept it on B, the number of beats became 6. Find the initial frequency of B, that is before waxing. Simple mental question. Okay. So the beats ka concept, right? We will see later on in Doppler. We can actually use beats ka concept to find the speed of the vehicle. Cricket में कभी देखा आपने? The ball is coming with a speed of 140 kilometers per hour. How do you know that precisely? Or let's say when a car is going or a plane is flying, it's called a frequency gun. You take that machine and put it towards the vehicle and you can find out the speed. So it actually uses the concept of beats. You'll send a sound wave that will go on the frequency, that will go and hit the car and come back. So the frequency which you sent and which comes back are different. Based on the difference in frequency, you can find the speed of the vehicle. That is a basic concept which we use in radars actually. That is how you find the speed of something which is coming towards you. So what is the catch here? Now the problem here is initially A ka frequency is 500 hertz. You said you're getting 4 beats, so there are 2 options. Either B ka frequency can be 496 or B ka frequency can be 504 hertz because the difference is 4. I don't know which one is big and which one is small. Now in both the cases, if I put wax and if I put wax, again I'm assuming this frequency will become, it will decrease, so it will become 494. This frequency will decrease, this will become 502. So in this scenario, you will get number of beats 6, which is right. In this case, the number of beats should have been definitely less than 4. Again, like I took a random number, so this is wrong. So my answer is 494. 496. Therefore, so initial FB is. So always you get 2 options, 496 or 504, you need to check. Is this clear, everyone? Let's see one more. Let's see one more. So waveforms of 2 beats as given. So the first beat form, wave, right? Waveform is formed by F1 and F2, use 2 frequencies, and this is the waveform. The second one is formed by F3 and F4. It is formed like this. Now both the time intervals is 1 second and 1 second. So I wanted to compare mod F1 minus F2 and mod f3 minus f4. Compare f1 and f3. So using these two waveforms, you need to tell me the difference who is bigger and who is bigger, f1 or f3. This thing I couldn't draw properly, but it is more compact. What do you guys think? The first one was easy. The first one, if you look at this in 1 second, this is a beat, right? Increase and decrease. So this is one beat in 1 second. This is increase, decrease, increase, decrease. So there are 2 beats in 2 seconds. This is nothing but mod f3 minus f4. And this is mod f1 minus f2. So the first one is clear. Now we don't know who is greater between f1 and f2. What about the second one? How will you compare f1 and f3? What is frequency? Number of waves per second. Now, can you tell me in both of them in 1 second who has more number of waves? I agree, waves ka amplitude change ho gaya, but how many waves who has? Can you see this thing is more compact, isn't it? There are more number of waves in 1 second, meaning go back to the derivation, you'll understand. Regularly, the wave should have been like this, isn't it? This wave became like this, no? Meaning the number of waves can't change. So in 1 second, if you see, there are more waves. So there are more waves here in 1 second compared to B. So F1 is greater than F3. You can even say F2 is greater than F4. So just to give an example, maybe this thing is like this. This is produced by 1000 hertz and 999 hertz. Very high frequency, but the difference is 1. Maybe this is created by 500 hertz and 498 hertz. Low frequency, but the difference is 2. Are you getting? So this waveform example is 1099. This waveform is 500 and 498. I hope you're getting the difference. So there are 1000 waves per second here. There are 500 waves per second here. But this amplitude is dropping in 2 times and this amplitude is dropping only once. So just check how many these things are more closely packed. So there are more waves. This is tightly packed. So there are more waves per second. Easy? Any doubts on this? Next one, try this as a homework. Next class we will discuss this. It's a good one. Instead of 2 tuning forks, if I use 3. F minus 1, F and F plus 1 are sounded together. This was a mains question long back. They simply asked find the number of beats per second. Now that's an easy one. But the moment I ask this thing, find the ratio of intensity of each beat. So whatever beats you, let's say if you get 3 beats, each beat will have a different intensity. I want the ratio of the intensity. This will make this question suddenly an advanced question. If it is a paragraph, I'll ask you these 2. So first find how many beats are forming. All beats won't have same intensity. So find the ratio of intensity of the beats. So meaning you will hear something like, something like this. It will be small sound, big sound, small sound, big sound. You'll have a variable intensity. So do try this as a homework. So next class when we meet, first thing we'll discuss. After this, we'll be starting with Doppler. In Doppler, it is removed from mains portion, but advanced scale abhi bhi hai, so we will do that also. Mostly next class we should wrap up mostly. It is 1:1:2. इतना अच्छा number नहीं आएगा. Try कर. So mostly next class we should wrap up the chapter, but if it gets a little more, we will maybe the other class we will take another half class or something. And then after that we'll start off with capacitors. We'll finish off capacitors and current, and then we'll come back to wave optics. So, okay, so with that we'll wrap up for the day. So any doubts, anything, you can stay back and ask, or else you're free to leave. I hope everyone is getting, especially today's class, right? There's a lot of weird things, you know, OrganPi, beads and all. I'll send you those videos. Make sure to try to understand. बोल रहा हूँ ना, ये chapter कैसा है ना, as long as you really understand and believe, this is actually happening, it will feel easy. Now that beats, right? I showed you everything mathematically, but if I didn't show you that beats ka sound, actually you wouldn't have ever believed it. You would have felt like, beats hai. Clear? And that organ waves, when I say that flame looked more interesting. So, okay, so with that we'll wrap up for the day. So, yeah, you have to believe.